I apologize for my cold. I'm going to start off by giving some of the history of how I got into this, and then talk about some of our recent work. So, I think, as far as I know, that the big impetus for radiation hydrodynamics was the work during the Second World War on bombs. And the main method that was developed at that time was flux-limited diffusion. And the first publication, at least in the astrophysical literature, was by LeBlanc and Wilson. And you can see from the form here for the fluxes that it has the right limits in the free streaming limit and in the optically thick diffusion limit, but it doesn't work well in between, and people have played around with all kinds of different ways of trying to do this, and it's still being used, as I'll explain in a few minutes. So I first got into radiation hydrodynamics actually because Ed Spiegel was my thesis advisor, and we did some work on radiative damping of sound waves. And while I was a student, I spent a summer at Sac Peak, and Jack Zerker taught me something about radiative transfer. And an important influence on this was Christie's article about pulsating stars from the Reviews of Modern Physics in 1964. I didn't get back to it for a while, but had a graduate student, Richard Klein, who I worked with on doing some non-LT transfer with just a two-level hydrogen atom, looking at the shock propagation properties. And then Oki and I happened to be sharing next-door rooms in Annapolis, Maryland, at a conference on fluid dynamics, and started talking with each other. And Oka had been doing these anelastic convection calculations and wanted to do compressible calculations, and I'd been doing 1D Lagrangian compressible calculations, and also had been doing some radiative transfer. And I explained one of the tricks I had for getting around the round-off errors at small optical depths. And so we decided that we would get together, and I came to Copenhagen to work for half a year, I guess, or almost a whole year, in 1986. And at the same time, I had talked to Dimitri Mihalis and said I wanted to was asking him if he was interested in doing any stuff on radiation hydro with me. And he said no, he was very busy, but there was this young guy in Oslo, Mats Carlsen, and why didn't I go work with him? So while I was working in Copenhagen, I also took some trips to Oslo and started working with Mats. And that's also, so both Oki and Mats have been my long-time and most important collaborators for this last 21 years. And it's just been a wonderful experience. I thank them both. So, what Christie did was he did a Lagrangian 1D calculation. It was nonlinear. It was an LTE. And he was looking at the shock waves in RLI stars, and he had these time-dependent calculations and gradually reached a more or less steady state. And that was improved upon later on by Hill, who then went on to an Eddington approximation. One of the big developments was the paper by Auer and Mihalis, where they explained that you could solve the Poincare equations in a much more efficient way than people had been up to that point, essentially by Newton-Raphson iteration, which was called compute linearization, and that was much more stable and much faster than the methods that people had been using previously. And as I said, I got into these non-LT shock dynamics with Richard Klein, who was my graduate student, who's now gone on to do other great things. And so we took only 5 frequencies. We used the Eddington approximation, but we solved the Poincare equations together with the dynamic equations. We did the dynamics explicitly for the radiation and the energy equation and the population equations we did implicitly. While this was going on, Oka had been working in Uppsala and had got interested in doing 3D radiation transfer. His first code was an anelastic code, just looking at the surface it was in on a Cartesian grid. And he had this idea of saving a lot of time by, instead of doing many frequencies, of doing a multi-group method where he binned the frequencies into 4 different bins depending on the magnitude of the opacity. And he used this kind of interpolation between a Rossum opacity at large optical depths and a Planck mean at the small optical depths. And he looked at just a few rays through each point on the surface. It was a long characteristic kind of method. He actually did this work in the 70s, although it didn't get published until the early 80s, right? And he published a whole series of papers with Dinas Robbins applying these calculations to various stars, looking at line profiles, at line bisectors, and it really worked very well. At the same time that he was, and the essence of this method is that you have this opacity which is a function of frequency, and you just bid it with and you take account of how many frequencies there are on each of these different bins. At the same time, Matthias Stefan was also doing similar kinds of things. He started off, instead of doing 3D, doing 2D axially symmetric calculations using the method of characteristics. And one of the early papers that I found, he was looking at the effects of CO, so that he had basically 2 different bins, one where he had the Rossum mean, and the other where he had also added the CO opacities. In '86, I started working with Oka, and as I said, we wanted to do a compressible 3D code, and he gave me his anelastic code, and he said, well, why don't you look at it and see how we could generalize this to be a 3D compressible code? And I looked at it for several days, and I came back and I said, we better start from scratch. Which we did, and in about 6 months we had a very nice modular vectorizable code written. It took about another year to debug, which OK did most of. And we started doing our calculations. And one of our first papers was in '89, and it was only 6 megameters wide and 3 deep, went from the temperature minimum to about 2.5 megameters below the surface, which we continued doing those things for a long time. A lot of people ask, well, how did we start? Well, a lot of people start from polytropes, and then it takes a long time to relax. We've always started from previous ones, so we took one of the anelastic calculations as an initial step and started running that. And one of the big things we found was the great anisotropy between the upflows and the downflows, that you have these slow upflows which are diverging from a small area below the surface up to the granules at the surface, and then they come back down and they converge into small filamentary downdrafts. And that same year I got started with MOTS, but I only worked with MOTS for about 1 month a year for a number of years in developing this adaptive mesh non-multi-radiation hydrocode using the Drury adaptive mesh algorithm. One of our first results was looking at the calcium bright points, and in that first paper we also showed the effects of different ways of treating the radiation on a shock. Since then, we expanded that code to include magnetic fields, and this is I think about a 15-minute sequence of G-band images that Max Carson calculated, both looking down at the center and off towards the limb. And you can see the hilly kind of appearance that also was just about that time that people at the Arnes telescope in La Palma had been finding. We had never looked off towards the limb before. And you see these things which look like the fact that also, in these later years, there were several other codes that were developed. One was the cobalt code, and one of the which is again a code that's been used for many different problems. One of them was looking at a star in a box, and these are some simulations that were done of the entire star metal juice showing, I think this is the emergent intensity curve. And, of course, Alexander Vogler also developed his Muram code, and this is an image of the vertical magnetic field component at the surface from one of his calculations. And you can see how it's all swept into the intergranular lanes and gets very swirly. There were several other methods that have been used to do radiative transfer. One is the moment method, where you look at the energy density, the first moment, and the radiative flux, which is the 0th moment, which is energy density, the first moment, which is the radiative flux. And then you have to close this system by relating the radiation stress tensor back to the energy density using some Eddington tensor. And this is stuff that actually Ed Spiegel published one of the early papers on. So basically, you have to have the equation for the energy density, equation for the flux, and you have to close that by this relationship between the stress and the energy density with some kind of Eddington tensor, and of course you have to decide what to take for these scalar factors. The flux-limited diffusion only looks at the equation for the energy density, so in addition to closing it by having an expression for the stress in terms of energy density, it also has to have an expression for the flux with this limiting factor. And it's never been clear to me why people just didn't add the extra 1 to 3 equations for the flux and get rid of having to have one more arbitrary relationship. It seemed to me that the cost is really rather minimal if you're doing this kind of thing. Of course, another way of doing things is to use a Monte Carlo method. This is a flow chart I found from one of the papers. Basically, you start photons going from different places in different random directions, and you follow them for optical distance until they get absorbed. And in a straightforward way of doing things, it suffers from the same kind of problems with lambda iterations. That is where it's really optically deep. Things relax very slowly, but you can speed it up in the same way as the accelerated lambda iterations by treating separately those photons which get absorbed within their own cell and those that travel to an adjacent cell. I found a comparison between a number of these methods, and this is the variation of HCl plus populations as a function of distance I guess it's a disk around, in a collapsing disk around a star. These solid lines are from Monte Carlo calculations. The dashed lines are from ALI, except for G, which is using motion. And so you can see that there's really quite a bit of difference depending on what method you use, at least for some problems. So, radiation hydrodynamics comes up in an astrophysics context in many, many different contexts, from the very small to the very large. My own work with Oka has been on the convection simulations, and currently we've been trying to get to larger scale. So we're currently running something which is 96 megameters wide by 20 megameters deep. So that covers all of the hydrogen ionization zone and all of the helium-1 and almost all of the helium-2 ionization zones. And it's been a bootstrap process. Well, first place, you have to understand it's fairly low resolution. It includes an F-plane rotation because at those depths you begin to get some effects of the rotation and you develop a surface shear layer. So far, it's non-magnetic. The resolution in the vertical is pretty good. It goes from 12 megameters at the surface to about 70 at 20 megameters, but the horizontal resolution is 100 kilometers, and that's pretty bad. And we started off by taking, as one of our old simulations, which was 12 megameters wide by 9 megameters deep, we extended it down adiabatically to 20 megameters and let it run long enough for the motions to work their way all the way down to the bottom. And we relaxed, the turnover time at 20 megameters depth is 2 days. So we ran this 12 by 12 by 20 megameters for 2 turnover times, and then we doubled it to 24 megameters plus a little perturbation. I'll explain how you do that. Ran that for another 1.5 turnover times. And then we doubled that again to 48 megameters. That we ran for 65 hours, which is another 1.3 turnover times. And now we're running the 96 again, starting from the 48, and letting it relax. So it's run long enough so that its thermal structure is relaxed, but the dynamical structure on these wide scales still has not. So this is a picture at the depth where our original 2.5 megameter calculations were. This is our 6 by 6 megameter run. This is the 12, the 24, the 48, and then this is the 96. So you can see that even at 2.5 megameters down, when you have these cell sizes which are of the order of about 6 megameters, they were just completely, you've got one cell within the 6 megameter box. Now we have many, many such. Deeper down, this is now at 8 megameters, where we started here at 12 by 12, it wasn't even big enough to actually hold one of these above it. This is the vertical velocity. The scale is in kilometers a second. Downflows are light, because we take positive down and negative up. So the dark are the upflows, and these light areas are the downflows. And when we go down deeper, we get structures that are about 24 megameters wide, and those are small supergranule sized things. We'll have to see how much bigger things develop if there's enough time that we run this now that we're much wider than that. So the way we do it is we take one of the small simulations, we double it in size. We also take that or another snapshot and stretch it. And we add a small percentage of the stretch to the double only in the surface layers to make our initial state. We find that if we start adding it throughout, it's way out of equilibrium when we get shock waves, which mess things up. If we add it at the surface, it then just takes a while for the perturbations to penetrate down. And over the years, we've made lots of comparisons between the simulation results and the observations. One of them is to look at the histogram of the intensity, and the raw calculations have this double peak structure typically. But if you then put them through the point spread function, and this was looking at a snapshot from the I guess half-meter proton telescope several years ago, they come out to be a very similar distribution. Another way of looking at it is to look at line profiles. If you just take the temperature fluctuations that you get from the convection simulation, but no velocities, you get a profile that's too deep and too narrow. But with both the temperature and velocity perturbations in the photosphere from the overshooting of the convection, you match the observed profile very accurately. That's without any microturbulence or macroturbulence or anything added in. But this average profile, which is this thicker red line here, is the result of many, many different things, lines from different locations, which are shifted in frequency, which have different widths. And so what's generally taken to be this micro and macro turbulence is actually just the convective overshooting motions in the photosphere. One of the other things that Oka did was to show that line bisectors are very sensitive to the correlations between velocity and temperature in the photosphere, and therefore a very good check on what's happening. And in those papers with Francis Robbins did a lot of comparisons of his inelastic simulation results with observations of various stars. This is a comparison that has been recently been done, and you can see that there's very good agreement here for the iron lines. The observed is the solid lines. The dashed is from our simulation. From the simulation with magnetic fields, though, you get a rather different profile. So clearly, this was a quiet sun observation, and you need a non-magnetic simulation. Here, the shapes are the same, but there's clearly a velocity shift, and that's probably the case because the lab frequency the lab wavelength is wrong. At the same time, Oka has done some other work looking at non-LT effects. This is for oxygen lines. And one of the things that they found is that looking at the center of the limb variations of the equivalent width is that when the oxygen abundance was reduced from the standard amount, they got rather good agreement between the equivalent widths from the center to the limb. But the LT calculations were actually quite far off. So the non-LT is important there. Another thing we've looked at is the velocity spectrum. These the black line and these red and bluish lines are from various observations. These horses and stars, these are from our older, smaller simulations, and these black stars are from the new larger ones, actually from the 48 megameter ones. And you can see that, first place, there's very good agreement. You can see also that there's basically a power loss slope in the velocity amplitude spectrum, with maybe a little bump here for supergranulation scales. But aside from the granulation up here and a slight enhancement of the supergranulation, there's no special scales. You're seeing all the way down to giant cells. They just have very low amplitude, but you actually see them. We've also looked at separating the convective motions from the oscillations. If you look at the horizontal motions from the simulations I showed in the last slide, they're essentially purely convective. Look at the radial, they're a combination of both a convective component and an oscillatory component. And the same is true for the NDI observations. And at the large scales, it's the oscillatory which dominates. The smaller scales, you're seeing primarily the convective components. And again, there's a small enhancement here at supergranulation scales. But you can see it's really still a very good power loss. We've compared the K-omega diagrams. This is from the simulation, from the MDI observations. The dashed line is the theoretical F mode. The modes are sparser in the simulation in the sun because this was only 48 megameters wide. Again, we've also looked at the time-distance diagrams. And again, the black line is the theoretical F mode. And you can see that there's very good agreement there. A surface shear layer does develop. Its magnitude, though, is about twice what's observed. And we're not sure exactly why, but we think it's because there's angular momentum transfer by the viscous flux, which is, of course, larger in the simulation than it is in the sun.
What are the units?
The units, let's see, it's 1/100 seconds. This is a slice through the 38 megameter wide simulation that was done by Chris Heinze at NASA Ames for us. Here's the granulation at the top. Again, you have these large-scale upflows which are diverging down below. Some of the downflows at the top just get stopped. Some of them merge into the much bigger downflows. You see here that there are indeed some swirls, and then these upflows are diverging everywhere. And as you come up, of course, the density gets less, the scale height gets less. You can't support all of the mass, so most of the fluid has to turn over before it ever gets to the top.
You also have a bottom convection zone?
What?
There is the bottom convection zone?
This is 20 megameters deep.
Yes, but there
That's
is
the
also at
surface.
the bottom.
What?
Structures at the bottom.
These things?
Yes.
I think that's just because he was including our ghost zones rather than cutting it off.
Or does it have to do with the visualization, perhaps?
What?
Maybe it has to do with the visualization technique, because there's tracer particles which are injected into the domain.
That's possible. I don't know. I don't know exactly how he did it. If you look at horizontal slices for the velocity at different depths, you can clearly see that as you're going down, the scale is getting larger and larger in a very continuous way. So there's no one depth where you can say, oh, that's... Yes, you can say that down here, the whole thing here is 48 megameters. Yeah, you have things that are of the order of about half the box size, 24 megameters, the small supergranules. But as you come up, you have the surface holes, and you get at the surface, and you have the granulation. So this is now a movie of going down with depth of the temperature. And now coming back up again. This movie that Oka made.
Why so many things with circular cross-section? At the surface it doesn't look that way, but as you go down, it looks like you're cutting through a vertical tube.
I think what you mean by the circular cross-sections are the downdrafts. Okay, the sort of cellular structure of the upflows is not a but you have fluids that are heading down. And yes, they do seem to have a fairly circular cross-section, and they have a ring vortex at their head. I think it's probably the vorticity which is keeping the head in fairly circular.
5 minutes.
What?
5 minutes.
Okay. That's about all. This is another one of Oka's movies showing that there's a very different time scale for the evolution at the different depths. You have a rapid evolution to the surface, a very slow evolution down deep. And you could see that same kind of thing happening with the vertical slice movement. This is another one that Chris Heinze made for us, where he's seeded streamlines at the surface. This is from a single snapshot, it's not in time. Here you have fluid that was moving up at the surface. So the dark is the surface, the light is at the bottom, and you see that the fluid that was moving up at the surface came from very small regions at the bottom because the upflows are divergent. Here you have fluid that was moving down at the surface, and you see that it comes down and outlines these largest cell structures at the bottom. And this is just the same thing, but now you're looking at it from all different angles. The interesting thing that I find in this is that the catch basin at the surface for these downflows is actually fairly well concentrated over those large-scale structures at depth. So it doesn't come from everywhere. The things, the intergranular lane downflows that you have over the centers of these larger scale structures don't make it down. They just get halted by the upflows at some point. Here, he's seeded field lines at the bottom, and you can see the stream lines. Again, you can see that very few of these streamlines make it up to the surface. Most of the fluid that starts at the bottom turns over way below the surface. And it comes back down in these downflow lanes that are surrounding the larger scale structures at the bottom. Now, if you just look at the intensity of the surface, if you look at a power spectrum, you see all of these scales, as I showed you. But if you just look visually, we don't see supergranulation yet the way you do in the sun. And I think the reason is because we don't have magnetic fields in yet. I think the magnetic fields play a large role in making the supergranulation so visible. This is the same kind of thing, now seated in the middle. Where the upflows and downflows have just been coated with the different colors. Finally, this is a movie that Wednesday1 made using time-distance analysis of the correlations of each point at the surface with the points at different depths at different later times. And so what you're seeing here are the waves which are generated at the surface. This is sort of like a Green's function. You're seeing the waves that are generated at the surface, which are probably getting down into the side and then coming and getting refracted back up again. So this is part of the work that he's done to analyze the local Healy seismology methods. And that's one of the big applications of these very large-scale simulations. Doug Brown and Charlie Lindsay and Sasha Kosovichev and Jim Lejeune have been using these simulations to check on their various methods. And with these 6 megameter wide simulations, also the ring diagram people will be able to use. So what do we want to do in the future? Well, we want to add in an active region. We want to look at quite some magnetic fields by feeding in a flux at the bottom. Possibly look at putting in a flux tube at the bottom and letting it rise. Chung has done this by putting in a flux tube close to the surface using Volta's code. But we think that if you put it way down at the bottom, it'll have time to actually get affected by the convection. And finally, you can use the results that we're getting as a driver for simulations of the chromosphere and the chromosphere. Thanks.
Thanks, Bob, for presenting us with this large range of lengths and timescales, which we have all been looking for, of course, over the last few decades, and now we finally see them. I was about to ask myself, is there anything else that you didn't really expect? That would, of course, be one question, but I think one of the most important values in this is perhaps to use these simulations as a tool to verify other observational techniques, as you just mentioned in the beginning, in the end, this ring diagram technique, for example, or other seismology techniques. But are there any techniques, any aspects from these simulations that actually are quite different from the old mixing links ideas that have been coming up, that we have been thinking in terms of?
You can, I think, always find a mixing length parameter which will give you the same entropy jump at the surface. The problem is you don't know what that value is without doing such a calculation. And of course, mixing length doesn't have any of the dynamics in it. It doesn't tell you about the overshooting either above in the photosphere or down at the bottom of the convection zone.
Yes,
To continue that question, can you tell what happened when you went from anelastic to compressible? What were the major qualitative changes that you saw in the outcome?
Well, the major one you saw is that you have the waves, so you can look at P modes. That is at least the biggest one that I noticed. Okay, probably may know some other things. I don't remember.
It's only in a very shallow layer that pressure really matters. So the anelastic approximation is of course perfect at that.
Yes, Hans?
You mentioned the 24 megameters, the size of the large-scale features we see in the deeper layers of associated with the superconductor cells. This indicates this is really a distinct scale that you see at these layers?
No.
Or is it
At each layer...
Repeat the question maybe
I'm sorry.
quickly for
The question was was why we see distinct scales at each layer, I guess. Is that correct?
Well, yes, the 24 megameters. And my next question would have been, do you have an idea of how it comes about?
Yes. Okay. The question was, do we see distinct scales at any given layer and why? And we think we understand it, and we think it has to do with the changing scale height as you go down deeper and it gets hotter. And it's basically mass conservation. So that if you have fluid coming up, it's got to turn over, basically, most of it has to turn over within a scale height. And so that basically sets the scale, given some other things which give you the ratio of the vertical to horizontal velocities, which don't change that much. So as you go down deeper, get a larger scale height, you're going to get larger scale. So there is a sort of more or less typical size to the upflows at any given depth. But of course, the magnitude of the velocities decreases as you go down and the density goes up.
Paul?
Let me get some sense, and perhaps you can add it, of to what extent the accuracy of the treatment of radiation affected the dynamics. And as you got more and more sophisticated with resolution and dimensionality and so on, obviously we learned more things about the dynamics. But I couldn't tell whether departures from LTE were crucial or how approximate the radiation field could be and still produce all the dynamics.
Well, Oka has actually run some calculation where there was only one vertical ray, and things aren't all that different, except that, for instance, you don't get the faculae in that case when you have magnetic fields, because you don't have the sidewall hidden. But the growth structure is very, very similar. I think Hans Gunther, you've also done some calculations like that, looking at supergranular scale some time ago. We just had a vertical ray. Again, the basic structure isn't all that different. But if you look at details, it matters. And Ryan Trampedich has now tried a completely different way of doing the radiation. And he finds for the sun there are some small differences in the photospheric structure. And for metal poor stars, there are very large differences. So how you treat the radiation does matter. And if you really want to know how much it matters, you have to at least take some slice and do a full treatment, which was done at some point in the past for the solar case to make sure that was coming up pretty accurately. But you'd have to do it for the metal poor stars too, just to make sure.
Are there observational signatures which are still unexplained?
We don't get quite the right center to limb variation. And we're trying to understand why. I think that's the main difference. Am I right?
Maybe brief. You may want to do a brief comment about the business with the oxygen abundance and heavy elements. That's perhaps also even part of the next talk to some extent, maybe.
I don't really want to say much about that.
But I mean, it's important to realize, I think, the impact that these type of simulations have had in the field of stellar astronomy, where for many, many decades people were fairly sure about the oxygen abundance or the abundance of heavy elements in the sun, based on simple calculations using macro and micro turbulence parameterizations. Now, with more realistic simulations, over the last 5 years, these have been changed by 60% or something like this. This is a major change. The abundances of the sun, and that, yes, and that, so it was a major, almost a scandal, of course, which is, I hope we will have a chance to talk more about this.
What it does is that it destroys the nice agreement that they had between the P-mode observations and the solar models. So instead of having half percent differences, now you have like 3% differences.
Right, with these words, let me thank Bob again. And we have the next talk ready by Remo Collet from the Planck Institute in Berkeley. He is talking about three-dimensional hydrodynamical simulations of surface convection in red giants.
Thank you, Axel. I'd like to thank first the organizers for giving me the chance to presenting the results, which are part of the work which I've been doing in collaboration with Martin Asplund and Frank Adapter. So first of all, a few words about the red giant stars and why I'll be interested in that. So red giant stars are well known to, according to our understanding of stellar structure and evolution, to have a large radii and therefore to be characterized by high brightnesses, which make these objects very good observational targets, not only for observations within our own galaxy, but also for galaxies in the local group. So these stars are, again, according to our understanding, we expect them to have large convective envelopes. So convection is actually reaching the surface layers, which ultimately affect the formation of the spectrum, where the spectral lines are forming, and where the emerging flux, stellar flux is actually forming. And we expect, therefore, convection to affect also the shape of the spectral lines and possibly also the strength and intensity of lines. So we expect these, expect convection and overshooting in the surface layers to have effects also on our understanding of spectral analysis and stellar abundances. So what we did in our study is to take the 3D radiative hydrocode developed by Altman and Bob. Basically it's a long-standing project, as Bob explained, between stars. And we simulate basically box, the strong box in the star case. So we take basically a small portion crossing the surface of the red giant, and basically located roughly across the optical surface, above the, it's extending above the optical surface and below that. And we presently run the simulations at a resolution, relatively low resolution. It's 100 by 100 by 125. And just to give an idea of the size that we are looking at, the physical size, this is a horizontal plot of the surface intensity of our simulations, and the size, the scale length is 1200 megameters by 1200 megameters, and it goes deep, typically deep by 600 megameters or 900 megameters according to the metallicity. So these are also the effective, the stellar parameters which we are concentrating on. So we span a range of effective temperatures and a range of metallicities from solar down to -3. So the importance of these models is that, first of all, that they rely on realistic microphysics. So we use a realistic equation of state from Mihalis et al. That's from '88, but it has been updated since then. And a non-gray radiative transfer scheme, which was originally developed by Oke in '82, and consisting of this opacity binning technique that Bob has explained in his previous talk. The opacity binning is constructed based on the continuous opacities by Gustafsson et al. And the line opacities from Proofs. So far, we are treating radiative transfer only in the LBE approximation, which is basically, I mean, it's still a strong approximation, you can say. And no much magnetic fields have been considered yet. So I'll skip this part because basically the qualitative picture of convection resulting from the simulation is very similar in a way, apart from the scale of impulse, to the picture of solar convection. So with a warmer and larger upflows, which are diverging at approximately across the when they cross the optical surface, and they converge into granular lanes, which then fall back towards the center of the star in dendrites. So what I'm going to concentrate most in this talk is actually the use of these convection simulations in model atmospheres for spectral information purposes. So what I'm going to talk about mainly is actually the effect of convection simulations in terms of the temperature structures as a function of optical depth. So I took here two snapshots of two different simulations, one a solar metallicity and one for a metal pool giant, metallicity -3, and compared basically this is the temperature versus the optical depth, and the gray shades are actually representing the distribution of temperature across the simulation at different depths, while the dashed line is the average model atmosphere constructed, the average temperature structure from the simulation, and the orange line here is actually the overplotted structure from a corresponding 1D Marx model, which extends, as you see, I mean, it extends only from an optical thin layer down to just optical value of about 100. But anyway, what you can see is that basically that while the temperature structure, the average temperature structure in the solar metallicity case is rather similar in 1D and 3D, or the differences are very tiny, can hardly be seen probably from a long distance. In the metal poor case, there's a striking difference, especially at the surface, between the 1D case and the 3D case. And the reason is, mainly it has been found out before in previous studies of convection in solar type stars, is that it has to be basically, it can be understood when looking at the heating and cooling mechanisms that are occurring in the 3D simulations. So heating and cooling basically are controlled by two mechanisms. One is the radiative heating and cooling, of course, and the second, in the case of the simulation, is the cooling due to the adiabatical expansion that is inherent to 3D simulation. So while in the solar case, you have basically radiative heating provided by the spectral lines, and that radiative heating is sufficient to compensate the cooling due to adiabatical expansion. In the metal poor case, lines are less strong, they are pure lines, and therefore adiabatic cooling takes over and the equilibrium is reached at a lower temperature. So this is it. This is expected to have an effect not only on the shape of spectral lines, which are affected by the convective motions, but also on the strength of spectral lines. So if we actually try to simulate and try to actually synthesize a spectral line for a very metal poor giant using the same abundance in 1D and 3D, we would get two different strengths. So the orange line again is the 1D Marx model, while the blue line is a 3D model. So by plugging in the same abundance, then you get the 1D model is predicting a much smaller, it's a much weaker line in the case of the iron line, while the 3D is clearly giving a stronger line. And the reason is simple. The neutral iron lines, for instance, which is an example considered here, are forming very high up in the atmosphere, very sensitive to the surface temperature, to the lower surface temperatures encountered in 3D model. So you expect iron 1 in an LTE, you would expect iron 1 to be more abundant than in 1D. So that gives rise to stronger lines, and translating it in terms of a spectral analysis, so stellar abundances, if you have a stronger line and you have to match a weaker line, then you have to reduce the abundance. So basically, your abundances in 3D will be lower. And another way of seeing this is we can look at, again, in 1D, we can look at the iron 1 ionization, the ionization fraction, basically. Well, the ionization, the fraction of iron 1 with respect to total iron across the 1D model atmosphere and across the 3D simulation. So here again in gray shades is the 3D model, while the continuous line is the 1D model. So you can see that the, roughly, it's relatively close to the optical surface on up to relatively thin layers, the 1D and 3D models roughly predict on average the same ionization fraction. So that gives basically small corrections for lines forming in these regions in terms of abundance. So they are actually slightly negative, because as you can see, the density predicted by the 3D models is actually slightly higher due to the inhomogeneities in this region. While moving basically to stronger lines, which are more sensitive to the uppermost layers, then you get different corrections. So you get basically, again, you have basically an effect where you switch from negative corrections, slightly negative corrections, to positive corrections. But the most striking effect is when going to a barometric proof case. So you actually have that, if you plot the same thing, so if you look again at the ratio of iron 1 to total iron, and you look at the 1D case, basically the 1D case, the 1D model is so hot that there's virtually no iron 1 predicted in the line formation region. While in the 3D case we have an interesting effect where we have a part of the hottest part of the 3D models, the surface of the 3D models are actually giving no iron 1 at all. But if you go into the sufficiently cool parts of the atmosphere, you actually have the opposite effect, where you build up. Thank you very much. You build up basically a lot of iron 1, and you have the effect which I was talking about before, that you have stronger, with the same abundance, you predict much stronger lines. So you expect the corrections to be much stronger in the case of the 3D model. And we get, when going to very low metallicities, we actually get differences by up to almost a factor of 10 in terms of abundance. So the same thing is also, again, is also occurring when looking at molecular lines. So as neutral species tend to be more abundant, also molecules tend to be favored, and the formation of molecules tend also to be favored due to the cool temperatures. So again, when going at low metallicity, we also expect the corrections to abundances to be much lower. So again, about the order of magnitude is about the same, so a factor of 10. So we did some tests because, of course, these results are strongly dependent on how realistic is actually the temperature structure predicted by the 3D model atmospheres. And one possible downside is that we are at this stage we're including scattering as a true absorption, which is a strong approximation. So in principle, one could ask the question: could this lead actually? Well, if we had to include scattering as a real scattering, so would this heat up the atmosphere again? So we couldn't do that, of course, in 3D, but we did that in 1D. We tested that. So the 1D models are actually treating scattering properly. So by treating scattering in the same way, we actually see that basically you warm up the atmosphere. So you would expect actually that the effect to go in the wrong direction. So we are actually confident that the temperatures are not cooler due to scattering. Another thing is also, has been posed many times, is the binning scheme doing the proper job. So what we did here was actually to test that. So we took 2D slides of the simulations in the solar case and the metal pool case, and we performed a full test. Basically, we studied the radiative transfer in detail for all frequencies for the complete ODF, and compared the radiative heating cooling rate from this test with the radiative heating cooling rate computed with the binning scheme. So we correlate the two things. So here's basically the radiative heating cooling rate due to the ODF and the radiative heating cooling rate predicted by the binning scheme. And we actually see that in the solar case, well, the correlation is not, that's clearly a correlation, but it's not exactly a one-to-one correlation, it's slightly skewed. So somehow, I mean, heating is less, there's less heating predicted by the binning scheme when heating occurs, and less cooling when cooling occurs. So there's a loser, there's basically the coupling between matter and temperature is a bit loose in this case. But in the metal pool case, actually the correlation is pretty good. So again, if there's a problem with a cooler temperature at the surface, it's probably not to be related to the binning scheme. So I think we're running out of time, so I'll have to skip. We did some tests with a non-LT calculation of the average 3D model. And just shortly, I can tell you that basically when looking at the iron one lines, the LT were getting stronger. So by studying it with a non-LT, with using the average model and a non-LT radiative transfer, then we would get actually the opposite effect. Due to photoionization, iron one lines would get actually weaker. So that compensates. But we are not yet at the stage where we can actually do this in full 3D. So that's basically about it on this subject.
Thanks very much for your interesting talk. And questions, please?
I didn't understand your argument about the scattering. I mean, you have an approximated 3D scattering in, and you test with a 1D, which is doing the scattering right, and you get deviations. Doesn't that tell you that you should better include some more realistic scattering?
Yes, certainly that's the thing, the way where to go. But my point was, I mean, we were testing whether the scattering was, treating scattering as true absorption was causing the surface temperature to be too low. And it's actually not the case. So when doing it, or at least what we did was doing the test with the 1D models. So when treating scattering as true absorption also with the mass model, then we would get actually higher temperature. So that was the test. But you're right that we should do the proper treatment of scattering with the 3D.
That's an interesting aspect that is perhaps useful also for the disk community. Scattering is probably extremely important too. But Mitch has a question.
Have you tried going down all the way to population 3 opacity, or are you planning to do that?
Sorry?
Have you tried going down to population 3 abundances, where you essentially have no metals at all?
Actually not. We don't have, at this stage, we haven't ODF for these population 3 stars, and we haven't even the bin version of that. So that's certainly something we have to go to.
Hans?
I just wanted to make a remark concerning these heating and cooling rates. In the end, I would like to know how much a temperature error is associated with these rates. And it's very hard to translate mentally some of the rates into a temperature change. I think we need to step that one should take at some point.
So the question was, how does it translate to into a temperature error?
Yes, we actually, in the plot, now it's not available anymore, I plotted the radiation, the heating rate, we normalized with gate capacity at constant pressure. So that gives an idea of what instantaneously the heating would be in terms of temperature. But you're right that that's not enough to predict what the difference in temperature would be in the final simulation. So that's it.
All right. So thanks very much, Remo. Very interesting. And now we have a collaboration that is led here by Oleg Kokokov, and collaborators include Bernd Freitag over there at the end and Nick Piskuna from over here.
Yes, thank you. So I would like to tell you about some preliminary results of our 3D aerodynamic simulations of convection in A stars, photostars that much photostars than we discussed until now. So A stars in general are quite interesting objects because these stars are unique laboratories for investigation of various effects which do not manifest themselves in other stars. For instance, strong magnetic fields or non-solar chemistry due to chemical transport processes. Also, A stars have non-radial pulsations, and rotation rates of these stars span a relatively wide range from extremely fast to very slow. It is a general opinion that convection is relatively weak in these stars, and this is indeed the case if we consider, for instance, the impact of convection on the structure of model atmospheres. But in fact, if one considers the fudge velocities that are usually needed in the abundance analysis, then it turns out that A stars have the largest microturbulence needed in classical abundance analysis. So here I show you the results of microturbulence as a function of effective temperature for dwarfs and giants. And as you can see, the position of A stars corresponds to the maximum for both giants and dwarfs. So although the impact of convection on the model structure is small, the motions are violent and velocities are readily observed in the atmospheres of these stars. And another very interesting observation by David Gray and collaborators is the existence of so-called granulation boundary. And this is the separation line in the HR diagram. For stars cooler than this line, typical C-shaped bisectors like in the Sun are observed. But somewhere around G0 in giants and F0 in dwarfs, the bisector shape changes completely to the inverted C-shape, like illustrated here. And the cause of this effect is completely unknown currently. And turning our attention to more recent observations, there was a very interesting paper by Lundstreet who collected very high signal noise observations of A stars and compared these observations with predictions of simple 1D LP calculations with fudge velocities, micro and macro turbulence. And he finds that while for early A stars, around 10,000, it is possible to fit observations very nicely with 1D models. For cool stars, one first of all needs to introduce a fairly large microturbulence to get the same abundance from weak and strong lines, and at the same time line profiles are really cannot be reproduced with 1D model and any combination of fudge velocities. And as you can see here, this deviation between 1D model and observations is very clear, and especially interesting observation is the existence of strong blue asymmetry in the line profiles, and the corresponding bisector span is around 3 kilometers per second. And these observations were obtained for non-magnetic A stars, AM stars, and for magnetic AP stars, the general opinion for many years was that the strong field, Kilogauss strength field in these stars fully suppresses convection. But this is not the case, as we find now. In fact, these stars show strongly stratified abundance, so different chemical elements are concentrated in clouds at different heights. And for these stars, we can probe, due to stratification, we can probe much larger depth, range of depth. So for the lines forming in the photosphere, there is virtually no turbulence present. But for the lines in the hyperspheric layers, in the layers which would correspond to, say, chromosphere in the sun, we see rather strong broadening of about 10 kilometers per second. And this broadening is modulated by non-radial pulsations. So when stars compress, lines get broader. And we initiated the project to address some of these issues with 3D and hydrodynamical simulations. It should be pointed out that such simulations for A stars are considerably more demanding in computation time compared to solar-type stars. And this is because radiative effects of radiations dominate, and therefore 3D simulations have to be carried out with small time steps. And this results in the necessity to spend 10 to 100 more computing time on A stars. And furthermore, A star models have to include simultaneously the treatment of small surface granulars and large deep convective cells. And furthermore, there is a strong temperature jump just below the photosphere in A stars, and simulations have to resolve it. So we are running Cobalt code, and this is basically the development of the work by Reitek and Matthias Steffen. And this is box in a star simulation, similar to what Remo just described, the giants. We are running both 2D and 3D simulations, and also comparing simulations with gray and non-gray opacities. We use the spectrum synthesis code by Nick Piskunov, which computes line profiles from the 3D snapshots in LTE. And then we compare observations with very high signal. We compare observations of AM stars with predictions of our theoretical models. And the span of effective temperatures and gravities that we consider now is these values from 7 to 8,000 Kelvin. This is comparison of the granulation pattern. This is continuum intensity at around 6,000 Ångström for the Sun and for the A-type star. The horizontal dimension here is comparable, so you can see that granules in A star are much larger. And there is also, for some granules, there are some bright borders, like here and here. But the overall appearance of the granulation pattern is fairly similar in the sense that there are small regions of downdrafts, but large regions of matter moving upwards. And the vertical snapshot shown here represents temperature with a color background and velocity field with the arrows. And you can see that there exist small scale convection motions in the upper part, but still large granules in the lower part. And at the same time, we have carried out some high-resolution 2D simulations which show rather interesting effects. So after simulations run for a while, the small-scale granulation merges into some kind of large downdrafts, and the supergranulation pattern, in a sense, emerges. And these are 2D simulations at fairly high resolution and covering much time. And it still remains to be seen if these effects are reproduced in the 3D simulations.
Well, sorry, but they can't, right? I mean, it's known that 2D turbulence conserves entropy, and therefore you have an inverse cascade. You always make large-scale structures in 2D turbulence.
Well, we don't know. We are working with the regime.
It's a theorem, I'm sorry.
Which was not,
But this also happens in
not
3D,
explored.
this large-scale stuff.
Not for this reason.
3D, yes, not here, but in calculation.
Okay.
So, yes, of course, you're right. In practice, this means that the vortex structure is much more extended in 2D horizontally than it will be in 3D. In 3D is more confined.
Yes.
That's one difference, yeah.
Well,
But maybe
here,
one point.
magnitude or so, but in 3D I would expect, I mean, we have
one video what I just want to show that for what we did to run and cover stellar hours of the projection for a camp, and it shows 1/8 of the depth. So the effort, the increase of effort is gigantic, and the increase in results is tiny. So there is not true that we see a large difference including in 3D runs for some weird reason. In 3D there will be some huge cells in the deeper length. It should be just a smaller extent, a factor of 1.5.
Anyway, there is much to explore here, and we are just using 2D simulations to map some of the parameter space, which is just not possible to cover completely. So what about the depth dependence of velocities? We see a fairly large contribution of horizontal velocity. So here the dashed lines correspond to the dependence of average velocity of the logarithm of Rosland optical depth, and the solid line corresponds to vertical velocity. And also different colors compare runs with gray and non-gray opacities. If we compare average temperature structure with the predictions of 1D models, and this is shown here, the red line corresponds to average cobalt temperature structure, and this yellow background shows the span of the 3D temperature stratification, including 95% range of the models. You can see that deviations from this average are very, very small. And the black line shows the Atlas 9 1D model with a convection treatment including the theory of conical aesthetics. And actually you will get nearly the same thing if mixing length with alpha 0.5 in the SU. So these results confirm many recent papers which suggested that in A stars, convection efficiency is actually less than usually assumed in 1D models. In 1D models, alpha is typical 1.25 or so. And now turning attention to line profile synthesis and comparison with observations, our main goal, we see that weak line profiles are reproduced fairly well. So here the observations are shown with the points, and the blue line corresponds to 3D simulations with the gray. I think gray should be red, and non-gray line is the blue line, of course. And you can see that the observations of weak lines are fairly well reproduced. And this is done for the first time for A-type stars, but at the same time there is rather poor fit to the wings of the strong lines. Obviously models lack some high amplitude velocities that are needed to explain these wings. And if we look at the bisectors, if we look at the intensity spectrum, this center for instance, we get a typical C-shaped color-type bisectors. But if we compute carefully the bisectors from the flux spectrum, disintegrated spectrum, it's no longer C-shaped, it's more of a straight with a weak blue asymmetry in the wings. So this contradicts what was said in the previous talk, that there is correspondence between the pattern, the topology of the convection field and the bisectors. We find that this is actually not the case. And in conclusion, these are the first 3D radiative hydrodynamics simulations of A-star convection with non-gray opacities. And these simulations confirm the idea that efficiency of convection is fairly low in A-stars. We had some success in reproducing profiles of weak spectral lines, but there is still something missing in the model, and we cannot reproduce strong lines, and we don't have high amplitude velocities that are currently needed to reproduce observations. What we are going to do in the near future is to explore parameter space in more detail, and we also want to include non-solar chemistry. First of all, AM stars with which we compare our models are known to be chemically peculiar. They have slight overabundance of metals and also helium depletion, and maybe helium depletion will modify the structure of the convection zone. We also think of including effects of magnetic field and T-mode pulsations. And then, of course, the major goal is to understand the granulation boundary and inversion of the bisectors in the entire diagram. This is, I think, a major challenge for 3D convection models. Thank you.
Ed, first question.
Should I say still, or you
Yes,
want to
please.
repeat?
Go ahead.
The issue I wanted to ask about is that you know that we show the players, etc., say that the anomalous abundances in many A stars are the result of radiative levitation. And the question I have is whether these large velocities, which by the way worried Lundgren already 50 years ago, would interfere with that explanation of the anomalous abundances.
No, there is no contradiction because in AM stars, according to most detailed calculations of radiated diffusion by the group of Schwarzschild calculators, the chemical transport processes which create anomalous abundances occur deep. They occur over the whole radiated zone, essentially, in the star. Whereas convective motions mix only the thin outer layer.
So the stuff just goes right through the...
Yeah.
Hans?
Do you have any indication about the location where this absorption in this absorption in the blue ring of the strong lines occurs? Spatially?
You mean location with depth?
Yes.
Well, this is very difficult to say since we do not reproduce this thing. How can we tell where it originates? But since it seems that the weak lines, there is no really agreement between the shape of the weak lines, observed shape, and the strong lines. So it is not just the scaling of these observations to that. Only strong lines do show this very pronounced blue asymmetry, and probably this is an indication that something is happening in the uppermost layers, to which on the strong lines, the cores of the strong lines are sensitive. That's the interpretation.
They also in the weak one.
Yes, but not to this extent.
Any other questions? Let me remind you that we have a discussion session before lunch, so if there are more general issues, and I have made a few notes already, there's a few general issues that we have to bring up. If there are other issues, please write them down. So, since there are no further questions, let's thank Oleg again. The coffee should now be outside the lecture room.